Okay guys, so this is a continuation for our lecture in shear design concepts, and I just like to make some valuable points on the use of the equations we have derived in shear. Okay, so basically we have two types of equation, as I have told you in my previous video. So this is what you call the detailed, no? The detailed equation, which is a rather not so long an equation, and this is for the SI unit and for the English units. No? So if you want to use SI, you just pick this one, and you want to use the English imperial units, you pick this one. And also we have the day-to-day equation, which is I termed as a simple equation that we may opt to use. No? So in SI it's only 1 over 6, and in English it's only 2.0 square root of FC prime BWT. Okay, so I'd like you to take a look at this plot. If I will plot the shape of the detailed equation, something like this will appear. Okay, so this is a detailed equation, and the simple equation is this one here. Okay, so the simple equation is only a straight line, while the detailed equation is rather composed of a flat line and then a nonlinear graph. And if I will compare the two equations here right now, I can say that since we are using or are looking into the capacity of your beam in shear, I can say that the detailed equation is less conservative than the simple equation up to this point of intersection. No? So at this point, there is a break-even point upon which your capacity determined by the detailed equation and the simple equation are just the same. Okay, they are just break-even. But at the left side, okay, at the left side of this vertical line here, you are assured that your simple equation is more conservative than the detailed equation. It's because you are given here a smaller capacity than in the detailed equation. And at the right side, we can say that your simple equation now is less conservative at this range. Okay, meaning to say, if you are going to look into some issues and concerns when you are dealing with safety, uh, you may actually look into these two uh, equations in that perspective. Okay, now which do you think is more practical? Of course, the simple equation is more practical to use because it's simple, while if you are doing some computations with the better accuracy, you might as well do the detailed equation. But since we are now in the computer technology, there's no problem using the detailed equation, since any formula, whether it is complicated, complex, or not, can be handled by computers. Okay, so that's the comparison I would like to give you as far as the detailed equation and the simple equation is concerned. Okay, so for the plot of the ACI equations, I already explained to you what this means, no? As far as your plot is concerned, but we are using here some mixture of variables, which is not directly a shear function. No? So here, your shear is actually implicitly mixed up with f square root of fc prime, and here also your shear is mixed up with a variable, let's say rho, square root of fc prime, and m. Okay, so there's a mixture. But I would just like to tell you that this equation above here, it was actually patterned or derived from this plot of this equation based on test results. Okay, so let me go now to the procedure on how to detail your uh, your stirrups. Okay, so that's another thing we have to bear in mind, how to detail your stirrup or lay out your stirrup. Okay, so let me show you now or share to you a sample plot of the stirrup or layout of the stirrup here. Okay, so can you see my screen, class?
Yes, yes, sir.
Okay, is my video okay? Is my audio okay?
Yes po, sir. Clear naman.
Okay, so this is now a layout of the stirrup. No, so if I have a simply supported beam, I think this problem refers or this layout refers to the same problem I have shown you a while ago. So if I want to lay out now the stirrups on the basis of uh, how and how many stirrups are needed, so I have to do it very systematically, because the spacing are only calculated spacing. I have to be practical in my way of arranging them. Okay, okay, so you do it now this way. So remember, the first thing we did was to take a value of your spacing, okay, at d distance. Okay, so what is this d distance here? This is the critical location for your shear. Okay, we got the spacing, calculated spacing, and then we got it from the formula S is equal to AV Fy or FV D times all over Vs. Okay, so remember that we did this one where S is the first stirrup spacing that we did when we get the critical Vs, considering your D distance here. Okay, and we get some value here, and that value is the one that is actually considered on your first stirrup. So take note that the first stirrup must be placed a distance 1/2 of your spacing at the distance. Okay? So kalahati, no? Sa face ng support. So in this particular example, the face of the support is not the face of the column, it's the face of the bearing plate that was provided to support your simply supported beam here. Okay? Not the face of the column. If there are no bearing plates here, then you can consider the face of the column. Okay? Okay. So after that, this is now your D distance. This 0.54 here is actually your depth upon which your S1 was computed. And take note that if S1 is less than, or sorry, S1 over 2 is less than 0.54, you still have to continue the arrangement of your stirrup within that distance of D at a spacing of S1. Kaya lang ang problema dyan, hindi siya magsasakto, no? So, mangyayari, you will stop at a certain point. Let's say, at this point, say S1 up to a D distance here you stop here, S1. Okay? And the remaining here will be continued on the next range of spacing. Okay, let's say S2. It so happened that at 1 meter, your S2 here is the same as S1 because what prevailed is the maximum spacing requirement on the ACI code. Okay? So you have to check on that, no? It so happened that your spacing here, S2, is greater than the maximum spacing requirement, which is also greater than S1 calculated at the distance. That's why at this point, up to very near your 1 meter, all you see are S1s, okay? You cannot see other values simply because this S1 pertains to the maximum requirement given by the code. Okay? Now, after getting it from 1 meter, remember what we computed. This 1.92 here is what? This is the theoretical distance x, in which what? In which your stirrups are no longer necessary or needed. No? Stirrups are not needed theoretically. Okay? So at this point, we solve for x, and it so happened that at this particular computation, your S2 is the one that prevailed. Okay? So dito, mag-start na yung S2, 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 S2. S2 must always be less than the maximum spacing allowed. Okay? So your S max based on your computation. Okay? So you stop again somewhere here. Okay? Here you stop at this point. I think here you have to stop greater than the allowed. So let's erase this one here. This is the 0.54. So the first stop of S1 is here, and then continue. The next stop is here, and then S2 here. And what is this 2.49 here? 2.49 is actually the X distance where minimum stirrups must be provided according to the code. Okay? So this is the minimum stirrup requirement. Okay? And the minimum stirrup requirement so happened is actually greater again than S2. That's why we use continue S2 here. Okay? Hanggang dyan. Okay? So, and then, of course, your S max must be provided on this remaining point. Okay? So, this is now the remaining area in which we don't have to allow no stirrup zone here. Some engineers they do not place any stirrup, but for reasons of further safety, we need to place at least an S max at this point. Okay, so that's how we arrange the stirrup, and then we count it, and then if you double it on this left and right side, you will come up with a 30 stirrups. So this is actually irrelevant to the construction workers. No, what is relevant for construction is this number of pieces. Yung ito hindi na nilalagay sa plano ito, no? Ang nilalagay na lang kung ilan yung stirrup na kailangan mo. Kasi hindi naman nila naiintindihan yan, no? Okay, so that's how your stirrup arrangement or stirrup layout is done based on the computation we have on the previous problem. So any question on this class? This is the practical side of what we have discussed from day one of our lecture in shear concepts. So any question?